Yeah, so welcome to the I don't know which lecture. So we discussed about the canonical ensemble in the last lecture, and there is a generalized canonical ensemble which is called the Gibbs canonical ensemble. So in this, your macro states are basically uh, the temperature. J is a force, and n is the number of particles in the system. So this is conjugate to some x, which is an extensive variable. For example, this can be a volume, and this would be correspondingly minus of pressure. So in this, your force is kept constant, and your this x is a random variable, and it can vary depending on uh, just like your energy was varying when you kept your temperature constant. So in this case, your Hamiltonian would be h, which is the internal Hamiltonian without any forcing, minus j, uh, I mean j. So this is the amount of work done by the system on the on the force to get to the value of x, and so you have to subtract this amount of work from the internal Hamiltonian, and so this would be the new Hamiltonian for the system, and so your probability distribution would be this. Yeah, this is the Hamiltonian without. So this would just be the e power minus beta h by the new z, and this h is basically h internal minus uh, jx, and this z. Uh, so mu s is the microstate and x is the, the internal variable. And so now to find this normalization constant z, you sum over all microstates and also over all the values of x, uh, this quantity. So this is so once you have this, now you can find the value of the average value of the x, because x is a random variable, just like we did it for the canonical ensemble and where we found the average value of energy, and this would turn out to be kBt log. So once you have this Gibbs canonical partition function, which is the z, you can find the average value of x by taking a derivative with respect to the force j, and from this you also know that g, the Gibbs free energy, is basically u minus ts minus jx. This is the generalized Gibbs free energy. You might have seen that you do plus PV over here. So it's the same thing when you have a generalized x. Uh, and once you have this, you have x equals minus del g del j. And from this, you get that g is equal to minus kt uh, ln z. So once you have your partition function, once you have calculated your partition function, you can find the value of the Gibbs free energy, and also you can find the value of the enthalpy. Enthalpy is just H is equal to U, so U minus uh, So you just subtract the work part of it, and so this you can calculate by taking a derivative of log of z with respect to beta. So you get h is equal to. So we can apply this to something called a grand canonical ensemble, where you basically include the chemical work. So you keep your chemical potential mu constant, and you allow your n to vary. So you have a system where your uh, you have a reservoir over here, and it can exchange particles with it. Just that the chemical potential in the system and chemical potential in the reservoir are the same. So there would be some exchange of particles, and so these two are in equilibrium. So you would have a fluctuating n, and you can find the average value of n. So this is grand canonical ensemble. In this, you have the macro states as uh, mu, v, and t. So you keep your chemical potential constant, and you and you do the thing. So for doing this, you would need to include the chemical work instead of the j dot x over here. And what is the chemical work? It is just mu times n. So for that, so finally you would get your probability to be mu s comma n. Yeah, this is the Hamilton. It depends on the microstate, and this also depends on the microstate. Yeah, the Q is called the grand canonical partition function, just like this Z over here. So you can evaluate Q in the following way. So Q is the grand canonical partition function, and this is basically sum over uh, n equal to 0 to infinity, uh, e power minus. So in this case, you have to sum over all these quantities over all microstates, right? So for that, for each n, you basically sum over all the microstates, and then you sum over n. So this is the quantity this is the only quantity which depends on n. So for every microstate corresponding to the number of particles in the system to be n, you sum this guy, and then you sum over all the n, basically, and this would give you the grand canonical partition function. And this guy, if you realize, it will be the canonical partition function with number n. So you can write. So this is basically just z uh, t n v. So, what is the probability of the system having a particle number n if we denote that by this? So that would be just this. You have to sum over all the microstates for given n. So that would be just this. This is a plus. Huh? Yeah, I'll just write. So the probability that your system has particle number n. So this was your probability distribution, right? This was the probability that your system has particle number n and it is in the microstate µs. So to find just the probability that it is at n, you have to sum over all the microstates. So that's what I'm doing. If you sum over all the microstates corresponding to that n, this will come out to be as the canonical partition function, and this is the normalization constant. And so you get this. What is? Beta is 1 by kt. So if you calculate the uh, value of average of n, that is basically 1 by beta times just like I had done for the previous one. And if you calculate the variance of this, or this would be basically n square minus uh, n square ka average minus n average square. This would be you can find this. I urge you to find derive these things based on the previous derivations. Um, and you can see that this clearly is proportional to n. So this scales as n. So your variance scales as n. So your standard deviation scales as root of n. So the relative error or relative uh, value of this n, delta n by n. So this is the standard deviation by this is the mean value. This scales as 1 by root n. So as your n tends to infinity, you see that this relative value tends to 0. So you will have a very sharply peaked uh, graph around n. So you will see your particle number to be practically constant. It will be fluctuating very narrowly around a heavily peaked minimum. So uh, in this case also you can find a thermodynamic potential just like the Gibbs free energy. So that would finally so you can find this. This is the grand so grand potential it's called, which is just u minus ts. And this is related to the logarithm of q. So right. So this kind of concludes the discussion of the various formalisms and various ensembles. So let us do some examples. Uh, okay, so let us see an example of the ideal gas in a canonical ensemble. So we can write the partition function of the ideal gas as we know that the Hamiltonian is just the sum of the kinetic energies, which is I equal to 1, 2, 3. So this would be 1 by n factorial due to the Gibbs counting, which I have told you before. And this h power 3n for the volume part. So the integral over qi would just give you the volumes. So you'll have one volume for each I, and this would be basically v power n. And these are Gaussian functions. If you see, it's p square by 2m in each of these variable of each of these pi. And so once you integrate that, you basically uh, beta is 1 by kt. So you finally, for one integral, you get this. For so when you do all the integrals, it will be a product of these terms, and so finally you get z to be this. So this is your partition function of the gas. And now once you have this, you can calculate all the free energies and so on from, and you can try to show that it's the same. It comes out to be the same as one we calculate from the microcanonical ensemble. So one more system I would like, which I would like you to see, is the quantized harmonic oscillator. So this system comes up like literally everywhere because physicists make everything harmonic oscillators. So yeah. So in this you have a Hamiltonian which is, have you seen this? Okay, so uh, you basically have, huh? Yeah, it's the ladder operator. So, okay, so it is basically half m omega naught x square plus p square by 2m, right? You've seen this potential, right? And so in quantum mechanics, you assign operators to each of these. And when you solve the Schrodinger's equation, h psi equals e psi, when you solve this, you get various energy eigenstates. So the energy eigenstates turn out to be this, basically. So you have various eigenstates, and each of the nth eigenstate has this in it, right? So now we can thermalize this harmonic oscillator, and we see if there is a particle in this harmonic oscillator potential, what would be the average um, level it stays in. You can do that. You can ask that kind of question. So for a single particle, and these states are not degenerate. So every energy E n has just one state. So particle can apply occupy. Uh, you don't have more than one state with energy E. So in this case, your partition function would just be basically sum over n. This for a single particle. So the first, uh, uh, so I am neglecting this half part, half h cross omega part. It's just a constant thing adding to the energy. So I'm not including that in the partition function calculation. So for n equal to 0, you have 1. Then you have e power minus uh, h cross omega by or beta h cross omega plus okay, and so on. So this is your partition function for the single particle. Is this fine? What is what? Uh, this is beta. So I'm just summing over the exponentials using the formula for partition function. And if you see this, this is a GP series. And e power minus beta h cross omega is less than 1 because it's, and so finally, and it's an infinite series, so the sum comes out to be this. Uh, so this is the partition function of your system. And suppose you have n distinguishable particles, you would just multiply the different partition functions, and it would just turn out to be one product of these. And now once you have the partition function, again you can calculate your free energy. Sorry, the yeah, the free energies. And so the free energy is minus kT log of z. So for this n particle thing, you will get n kT log 1 minus e. So this is your free energy. And what is your average energy of the system? This is minus. So this comes out to be n h cross omega naught into, So this is your average energy of the system, and for a single particle, you would have this to be the average energy of the system. And what is the average state in which it is residing? You just cancel this h cross omega factor, and you will get the average value of n to be 1 by e power. So, given a harmonic oscillator, which is uh, like in a thermal bath, you would have the particle to be on average on this state, on this state n, given by this quantity. And right, so this concludes the examples. So let's see. So now, once we have this formalism, you might ask, what is so difficult? So, given any system, you can always calculate this partition function, and you can find its properties. But it turns out that calculating this partition function is notoriously difficult, and like even the best computers take a lot of days to find these, and you have many approximation techniques to find these partition functions. So I'm going to show you a perturbation series or something uh, of sorts, which tell you how to calculate this for certain type of system. Are you done with? So let's suppose you have a general system which has a Hamiltonian H naught. This H naught has, the partition function with this Hamiltonian H naught. If you had this Hamiltonian, you could calculate it. And it has a potential. And when you have this total Hamiltonian, calculating the partition function, it's uh, suppose not possible analytically. So one thing we can do is, let's just write down the partition function. This is 1 by n factorial. So this is the form of the partition function, and you want to calculate this quantity. So if you see this, this is basically an average of this with this Hamiltonian. So this is basically, this is the partition function with this H naught Hamiltonian, and so and multiplied by the expectation value of this exponential quantity. And this exponential is taken with respect to this uh, original Hamiltonian, which is right. So in this, you multiply by multiply by z and divide by z first. Now you take this z inside here. So multiply by z naught, and this is a probability density exponential minus beta h naught by z. And with this probability density, you are taking the average of this. How do you take average of any quantity? If you have a probability distribution, is this fine? So so what do we have to do? We have to find somehow try to find this quantity, right? So let us do some more probability before this. So if you are suppose given a probability distribution Px, you can define this quantity called Pk, which is just the average of e power I kx, and this is just the integral of dx. This is like the Fourier transform of Px. So uh, now once you have this quantity, you can invert this Fourier transform. You can always invert a Fourier transform, and you can get Px in terms of Pk. So Pk contains all information as it contains the same. Oh, sorry. Pk contains the same information as Px, and we can Taylor expand the c power minus ikx inside. So Pk comes out to be uh, sum over and this is just basically so these things are called the moments of the probability distribution, and yeah, and so your pk has a expansion in terms of the moments, and this yeah, this is minus ik. Okay, so now let's define this thing called a cumulant generating function. This is just log of this is called the cumulant generating function, and this this has an expansion in powers of k, and let's call the so whatever the combination of x's come over here, we call that the nth cumulant. So and so if you know the Taylor series of log of 1 plus epsilon, it is basically just n equal to 1 to infinity. So you can apply this log of 1 plus epsilon expansion to this guy, because you know the first term is just 1, and you apply this to this guy, and you collect all the terms which have k power n, and whatever term remains over here, you call that the nth cumulant. So this cumulants are related to the moments, obviously. So the first cumulant comes out to be same as the first moment. Second cumulant comes out to be the variance, which is this in terms of the moments. Third cumulant is called the skewness. This comes out to be and so on. So is there a so there is a general formula for the nth cumulant. So you can also do one thing, that you can invert these relations. So you can write the first momentum in terms of the first cumulant, the second moment in terms of the second cumulant and the first cumulant, and so on. So you can invert these relations, and there is a relation between the nth moment. So once you put this thing in the sum, you will get this relation, that this nth moment, mth moment comes out to be. Okay. Okay, so just a minute. So these pn's are such that sum over n pn is equal to m. So all this, you have to sum over all the sets of pn's, such that this equation holds. You have your total. So your you want the mth moment, and you are finding that in terms of the nth moment, nth cumulant. Sorry. So the sum of all the n's in a given term. So this is the sum of many terms. In a given term, your sum of the n's would be basically equal to m. So if you have the nth cumulant pn times, you would have to sum over all these things, and that should be equal to m. And you have to so this has a diagrammatic representation. I can show that to you. Yeah, this is a summation of all sets Pn such that this is true. So, for example, let's try to calculate x power 4 moment. So, what do? We make 4 dots, and we make a cluster. So, this is a cluster of 4. So, in this, you have n equal to 4 and Pn equal to 1. So this fits this equation. You see that Pn 1 times 4 is equal to 4. Here m is 4 plus. Now you have uh, what are the other ways you can cluster it? You can cluster it in this. So here you have n equals 3. So there is one cluster with n equals 3, and there is one cluster with n equals 1. Is this fine? What other things? You can do this. So this has n equal to 2, and there are 2 clusters, right? And you have uh, two more terms. So you have 2 clusters of n equal to 1 and n equals 2, pn equals 1. And last you have 4 1 clusters. So that's n equals 1, pn equals 4. So now each of these has a coefficient. Each of these things has a coefficient, and How do you find the coefficient? You find the coefficient using this formula, that basically this thing, m factorial into. So this tells you the number of clusters possible for this given uh, for a given Pn and set of Pn and n. So let us apply this to this. Here our m factorial is 4 factorial, and you're summing over you're doing a product over n. So first you take n equals 3. So what is Pn? Pn is 1, so 1 by 1, and n factorial is 3, 3 factorial, and Pn is 1, so power 1 into, now n, you take n equals 1, which is 1 by 1 factorial. So this comes out to be 4. And so the coefficient of this term is 4. Similarly, if you do it for this, you you have you have just one n in this case, n equals 2. So m factorial is 4 factorial into 1 by Pn is 2, so 2 factorial, and n is 2, 2 factorial power 2. So this is 24 by 2 into 4, which is 3. So the coefficient of this term is 3. So do you understand the process of finding the coefficient? So the coefficient of this comes out to be 6, and this comes out to be 1, and this also 1. So can you give me a combinatorial reason of why this formula is valid? This is the number of ways you can cluster this m points into these given n and Pn. Huh? So let's say that there are m points, and you have n equals 3 and Pn equals 2, P3 equals 2. So that means there are 3 clusters. So how many ways you can arrange these? So uh, and then the remain, and so this situation is that n equals 1 and P1 equals 2. This is the situation, right? And this coefficient gives the number of ways you can distribute uh, uh, between these particles, such that you have this set of clusters. You have 3 clusters and 1 cluster. Can you give me a combinatorial reason why this should be true? So you can see that this m factorial is the total number of ways you can arrange all the particles. Then divide by this yeah, so in a cluster all the particles are identical, so you divide by n factorial, 3 factorial, and then there are Pn number of same kind of clusters, so you'll have a power of Pn. And this Pn, because these two are identical blocks, you can, so that would have a double counting, and then you product over all these n's, so that would give you the number of ways you can cluster. So is this fine? So if you have a joint probability distribution of px1 xn, I call that as a p. So this is a joint probability distribution. you can define a joint characteristic function defined by this k vector. Now you will have a k for each of these x1, and this is just the expectation value of exponential sum over. So this is how you define the characteristic function for um, n a joint probability distribution, and the joint cumulant function would be just log of this new characteristic function. And from this, you can observe, if you do the Taylor expansion, you can observe that so you take these derivatives first with k1 n1 times, k2 n2 times, and so on, and you take the derivative of this function pk, and you substitute k equals 0. So then you finally get the this moment x1 power n1 times x2 power n2. Similarly, if you do if you take this derivative of log of um, uh, this would basically give you a similar cumulant. So this would give you x1 power n1, x2 power n2, xn power. So if you take the derivative of the of the cumulant function, the same derivative of the cumulant function, you would get this cumulant where you have the same powers, but just it's a cumulant. And so again, you can do this kind of expansion. So let's say, for example, you want this moment x1 square x2. So you have basically two variables x1 and x2. So and you have like you are finding a third order moment. So you label by three particles, label this by 2, and label these two by 1, because 1 has square and x2 has is just for 1. And you have, so now you take various clusters of this. So this is one cluster, this is one cluster, this is a cluster, and so these are the four kinds of clusters possible. And if you see this one, there is just one way of clustering it because you have taken one and two are distinguishable. In this, you will see that there are two ways because you can have two with this one or two with this one. So this has coefficient two, and this one has this one because you don't have any you have just one single clusters, and this one will also have one. So and this corresponds to basically huh? Yeah, sure. It's one square c times this one is x1 and this one is x1 square star x. Oh, these all are cumulants. So the left side are moments, the right side all are cumulants. Oh, sorry. So is this clear? So let us come back to StatMech. So remember we had z equals z naught. So now you can expand this exponential, and if you remember the or let's take z, log of z. So this is the free energy, right? And so this is equal to log of z naught plus log of. So what does this look like? So this pretty much looks like the cumulant generating function, right? Uh, just that the ik is substituted by minus beta, and so you would have a power series of beta. So ln z would turn out to be this. Where this is the Lth cumulant. You had ik over here, uh, uh, minus ik over here, but here you have minus beta, so you just replace it with minus beta over here. So so you see this is like a perturbation expansion of z in terms of z naught and the higher cumulants, and also if you have any any measurable quantity O, which depends on PQ, for example, PIQI, and you want to calculate its average value. This is just 1 by Z exponential of minus beta U, and there is this O. So now you're taking an average of O times beta U, exponential minus beta U, with respect to this H naught. So this is just O times exponential. All these expectations are taken with respect to the H naught Hamiltonian. So if you see this thing, so if you just calculate this quantity, it is basically I times 1 by x. And this I and minus I cancel, and this ik exponential ik or not. Um, okay, so this is for k. Define this for k equals 0. So when k equals 0, this exponential ik, this becomes just 0, and this also becomes 0. This comes out to be O. So this expression is just basically this expression. So for calculating the value of average, you can calculate this quantity by taking, and now this quantity has a, this looks like a cumulant generating function. If you see log of exponential average. So, uh, so now you can again expand this in a perturbation series. This is equal to sum over L and L prime equals 1 to infinity. So you have this expansion uh, of your any average of any operator, and now you have this thing that suppose your H naught does not depend on Qi. So suppose your H naught was just sum over the kinetic energy Pi square. So then your UL, this is the moment. This moment is just because the integrals over Pi just give a constant. You would have just an integral over because doesn't you just depends on Q and not P. You would have just an integral over Qi, and the normalization would be the V. Why would the normalization factor be V? Why? Yeah, so this is an average over the original H naught. So you're not doing over the whole thing. So that's why you have the V. So this is something better to compute rather than the initial value of Z. So you can compute this value of moments and then go from moments to cumulants and then try to substitute that in the perturbation series, and you get different orders of values of the partition function, and so on. And you can find the moments like O times O power L times U. uh, if O is just dependent on Q and P, that makes it easier, but if O is dependent on both, that again troubles you. so this is a perturbation expansion, and so you see this kind of expression comes in various places. We might be going into describing stuff like fields, uh, stuff in terms of fields, and you would have a similar expression uh, 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 with the corresponding quantities in terms of fields. This kind of expression also comes in quantum field theory when you're trying to calculate field amplitudes, and yeah, so there is an intimate connection between all these uh, field theories and the stats. Okay, and also I would like to mention that if you have a dilute gas where your interactions just depend on neighbors, so U Q1 to Qn is just sum over Qi minus Qj, sum over I comma j, such that or you can say I less than j. So this would be the total. You just have interactions between two particles at a time, and the total potential energy of a dilute such kind of gas would be just the sum over all these pairs of interactions. And if you substitute these things into the cumulants, you finally get the something called the bireal equation of state for a general gas. So that is a sum over many terms with increasing powers, right? So if you do this expansion, you get this bireal equation of state. So next thing we do is to describe a solid, a harmonic solid. And why we are doing this? We are trying to transition from particle picture to field picture. And so this solid is like a crystal, and it has uh, the general Q is just a sum over some, and these are the lattice constants ABC, lattice vectors, and any Q, you can go to any Q in the lattice by this. Now, once you have this perfect lattice, if you have a certain temperature T, you will have basically vibrations in this lattice. By vibrations, what do I mean? These atoms are vibrating about their mean position, which is located at this Q. So there would be a certain Q plus UR. So each of this lattice position is vibrating. So in general, the atom at the rth position will have this displacement from the mean position. And why am I calling it harmonic? Because the potential energy of these vibrations from the lattice is basically approximated as a harmonic potential. And so you have this V is this is the equilibrium V plus, so since you have three dimensions, alpha goes from x, y, z, and beta also goes from x, y, z. And this is a matrix which couples uh, the displacement in the x in the beta direction and the alpha direction. So this term contributes to the potential energy of the system. So for example, this could be like k11 times u x square plus k12 times u x u y and so on. So these are the contributions to the potential energy, and all of them are quadratic. That's why you call this a harmonic circle. So now what you can do, you can do some. Uh, so you would want to diagonalize this thing and take it to a form where you can uh, separate different modes out, and then each of them will be independent of each other, and you work on each of them independently. So for that you go to a Fourier basis where you have, so you can decompose your displacement at each position r, because your positions are discrete. uh, your wave vectors will also come out to be discrete, and you basically sum over these things. And now if you substitute this over here, you can basically show after some manipulations your total so what is your total Hamiltonian now? It is basically 1 by uh, uh, r plus, this is your total Hamiltonian now. When you do this substitution uh, of this thing, your Hamiltonian will kind of separate out. It would come out to be sum over pk square by some capital M plus some k alpha beta, and this will depend on general R, uh, times q. So you have, and this is sum over k and alpha beta, right? So you have basically a sum over many harmonic oscillator type potentials. Each k labels a harmonic oscillator type potential, and now all of them are just sums, so they are independent of each other. So you can treat each of them separately, and you can apply that thing, that 1 by e power minus beta. If you quantize this thing, and you can apply, uh, this is the average state in which each of these oscillators lie. This omega will be depending on k now, because each thing depends on k, and then you will have basically a sum over all these things. So this is how you would approach it in a particle manner. Yeah. K is called a wave vector. That's how you do Fourier transform, right? Uh, so this is a discrete Fourier transform, because your thing is, you have a translational symmetry, but it is not, uh, you can't do any general translations. It is just symmetric. Just only translation by these amounts will take you to another lattice position. So it is periodic about that. Just so okay. So if you have a periodic function in one dimension, some periodic function, and it has a time period t, you can write it as a Fourier series, right? So that is a sum of omegas, with terms with omega 2, omega naught, and so on. Similarly, you will have a sum with of different k's, because here it is a three-dimensional periodic type of thing, and uh, these k's will be restricted to something which is called a Brillouin zone, because you can't go lesser than this a amount of distance. So if you have a single chain, so how will these modes look? These uh, modes will basically look like these sinusoidal things, with nodes can only be on the particle. So your wavelength can't go lower than this a. So this sum will be restricted over certain region in the, you call a reciprocal lattice space. Reciprocal lattice space. So each of these lattice points each of these planes in this lattice corresponds to 1k. It comes out to be like that, and you can these set of all k's form a lattice. You can, just like set of all r's form a lattice, you have set of all k's form a lattice. That is in the k space, and in that k space you would have a certain region over which you would need to sum this, and that would just uh, so that is how you do the Fourier. And that Brillouin zone determines this, how this omega will be dependent on this k, and you will know how many values of k have the same omega. Huh? No, you're assuming it has a translational symmetry with such a certain period a, b, c. What do you mean by symmetrical lattice? Okay. So this kind of thing you do, this approach is from a particle point of view, from the microscopic point of view. But this kind of approach is not always possible. And I mean, if you study condensed matter physics, this is done in a great detail. But we can do one more thing, which is called coarse graining. So at low temperature, suppose you have a chain of particles. At low temperature, you will have like low energy excitation. So having very small wavelengths is very unlikely. So you would basically have long wavelength excitations because each of the particles would displace in a small, and they would not, they, with respect to each other, they would displace in a small amount, and that would cost less energy. So you would have basically long wavelengths. So your lambda would be greater than a, right? And so let us consider this chain of particles, and let us consider an element dx, and this dx is greater than a. It is macroscopic in comparison to the lattice size, but it is smaller. It is much smaller than the wavelength. So this is a macroscopic infinitesimal element. And what is coarse graining? It is basically averaging over all the small wavelength modes. We are neglecting those, and we are assuming that our u. So now we define a field, which is phi of x, which is a displacement at each x, and we are assuming that the displacement does not vary much in this dx field because of, so this is a thing called coarse graining. You had a microscopic field ur, and from that you're going to this phi x ux u, I don't know, r. What was I writing here? Okay, so now once you have coarse grained this, you have a field defined at every so what is a field? It is something which varies in space, and so this is a field. So now we have to construct its Hamiltonian, and its Hamiltonian needs to respect the symmetries of the uh, internal organization of the atoms, and so on. So first, we have a kinetic energy term, which will be just del phi del t square, and so this would be a kinetic energy term. And what is rho? Rho is mass of atom uh, per unit length. So this would be a kinetic energy term which we include. Next, you have to construct the potential energy for the system. So the potential energy will be a functional uh, phi. So a functional is a quantity which takes in a field and gives you a real number. So this takes in a field in all positions x, which is spread over all position x. Okay, a functional is a quantity which takes a function and gives you a real number. And this phi is a function. This v will give you the energy corresponding to this function. And So one thing we require for if our interaction forces are short range, then we would not have non-local effects. So this part would not be impacting this part, like this particle would not be impacting directly. It would probably be impacting through other particles, but it won't be impacting directly. So you can assign a density of this this potential energy to this to every location x. Is this fine? So let me call that capital phi x, and that would in general depend on phi x, uh, and so on. It would depend on its in on the value of phi x on its other derivatives, and uh, this shows that. And since non-local effects can be captured by including all higher order terms, the if your system is local, if it satisfies the locality, your higher order derivatives don't contribute much to this potential phi. If you have the potential energy is depend on the separation between these two, the relative separation between these two. So this is ux plus a, and this is ux. So the potential energy will be dependent on the difference of this, and if you cosine this, this would be proportional to the derivative, right? This divided by a times. So you would have the derivative dependencies and so on. Okay. So this is the general thing. And then the system has a symmetry. It has a translational symmetry, which is that phi of uh, so so if you displace if you translate your system, uh, like increase your phi by a constant amount in each point, you're just basically translating your system. So this should not change your energy, right? All your energy will only change if the if there is some inhomogeneity in your translation, and you have a gradient or something like that. So this is a symmetry, and since this is valid, your phi cannot depend on phi x. This symmetry is constraining the fact that your capital phi cannot depend on phi x. If it depended on phi x, then this would not be true, right? So phi depends only on del phi del x and all the derivatives. The next thing is that the system needs to be stable at the equilibrium. So there is a equilibrium we assign, and with respect to that we are doing we are doing the small vibrations, right? So at phi equals to 0, you should have an equilibrium state. So that means the derivative of phi should be 0 at phi equals, the derivative of capital phi should be 0 at phi equals 0. And if you have linear order terms, the linear terms will just give you a constant if you take a derivative once, and that won't be 0. So you need the linear terms to go to 0. So phi cannot have any linear order terms. So, what is the lowest order uh, term in this expression of this potential energy? So, your density would basically say your potential energy would basically look like this. Is this fine? And so these are the increasingly higher order terms in terms of the derivatives. And so the lowest order Hamiltonian would be, and also for stability you require that you have a minima, right? So this coefficient k needs to be positive. So have you seen this kind of thing anywhere? Okay. So when you have a stretch string, what is the energy of the stretch string? Okay. So this is the lowest order uh, term, and yeah, and now you can use this Hamiltonian to find uh, the partition function and find the free energy. So what is the partition function? The partition function z is basically, so this is a path integral. So you define or it's a functional integral. So you are basically integrating over each function. This value, so this guy is like a this guy is a gives a value for each function, and you integral over all the functions, and that would give you the basically the partition function. Is this fine? Repeat. Okay. So so what is your microstate over here? The phi, right? Phi as a function of x. Now for different values of phi x, phi as a function of x, you would have different values of this e power minus beta h. To find the partition function, what we are doing, we are integrating over all the microstates. So here we have to integrate over all the functions. What? Oh, so this is not a normal integral, right? It's not a normal dx, right? So this is an integral. So this is a measure for a uh, or this. How do I say this? So this is a differential of a function, or you can say that. So you have a function space of functions. Any point in this as a function phi 1, phi 2. and you have some way to integrate in this. And so each function is now corresponding to a real number over here. uh, uh, that is what a functional is. And then you're in so for each function you take a small d phi, and then you integrate over this, and this would finally give this partition function. uh, so in a small d you have a normal real space dx, and from that you're going to a another real space. While you're doing this integral, you have a function space. From there you're going to a real space. I think it's enough for today. Okay.